So in this problem, we're told that a flywheel of mass m equals 5 kilograms and r equals 0.5 meters is going to be in some way attached to the wheels of a car so that it absorbs the kinetic energy of the car so as to make it easier to accelerate after braking. Now, at first we're asked what the mechanism of connection between this flywheel and the car could be. That's really not related to the physics, so I'm not going to answer that. But I'm sure that if you Google it or think about it a little bit, you can come up with a sort of a plausible answer. So all I'm going to do is I'm going to solve the physics of it and answer how fast it would have to be rotating in order to absorb the energy of a typical car. So first of all, we're going to calculate the moment of inertia of this flywheel. We're going to assume that it's most of the mass is at the edges, so its moment of inertia is going to be approximately that of a ring, which is mr squared. And so that's going to be just 5 over 4 kilogram meters squared. And so, of course, we know that the rotational energy of an object, K, is going to be 1 over 2 I omega squared, which in this case is just going to be 5 over 8 omega squared. I'm going to drop the units just sort of for convenience. So now, what we want to do is we want to figure out what the typical kinetic energy of a car is going to be so that we can then use that to figure out how much kinetic energy this flywheel is going to have to absorb. So a typical car is going to have mass of about 1 ton, or about 2,000 pounds, which is going to be about 1,000 kilograms. We're going to say that the car is going to have a velocity of about 40 miles per hour, which if you multiply by 1,600 meters per mile, and then divide by 3,600 seconds per hour, you get approximately 18 meters per second, which I'm going to round up to 20 meters per second. So then we get that the energy of a typical car, K, is going to be 1 over 2 mv squared, which is going to be 1 over 2 times 1,000 times 20 squared, which is going to be 200,000 joules, or 200 kilojoules. So now all we have to do is use this formula up here to figure out what the angular velocity of the flywheel would have to be in order to absorb 200 joules. And so that would be 5 over 8. We know that the units are the same because we put kilograms meters squared up here, which is exactly what goes into a joule. So 5 over 8 omega squared equals 200,000. So this tells us omega squared is equal to 1.6 times 10 to the 6 over 5, which is approximately 300,000 radians per second. So now all we have to do is we take the square root. Omega is going to come out to be somewhere in the neighborhood of about 550. 500 squared is about 250, is exactly 250,000. So I'm going to round up by about a factor of 50 to try and soak up that extra 500,000. This is a very rough estimation. All of these steps are sort of very hazy. You could do a much better estimation if you wanted to, but we're just trying to get a first order approximation. So omega is about 550 radians per second, which if you divide by 2 pi comes out to approximately 100 revolutions per second. And since there are 60 seconds in a minute, remember 2 pi is just 6.28, so that's approximately 5.5, give or take quite a bit. So this is, again, a very rough estimation. So 100 revolutions per second is equivalent to 6,000 revolutions per minute. So this flywheel would have to be moving very, very fast in order to absorb the energy of a typical car braking.